watching us from space. For the last 2 decades in high-resolution detail, watching our every move. The clouds and aerosols, winds and hurricanes, forests and cities, droughts and floods, the ocean currents and plankton, life in the ocean and on land. Land cover, aerosols, chlorophyll concentrations, wave heights, ozone concentrations, atmospheric moisture, the human footprint, sea level change, and temperatures and moisture in the soil. Now scientists have a high-definition data set spanning 2 decades to study and to learn from.
Well, NASA has a fleet of satellites that are always measuring Earth. They're looking at land, oceans, atmospheres, ice all together. The particular visualization represents the measurement of all life on Earth over 20 years. I personally find it mesmerizing. You're watching the Earth breathe here. The seasons are changing, ice is coming in and retreating. You can see the forests on land in green, expanding and contracting. You can see the deserts moving to the ocean. You can see biological deserts in the centers of the ocean, represented by blues and purples. And then as you look farther north in the Atlantic or towards Antarctica, you can see these greens and yellows. Explosion of life in the ocean, just like on land in the spring and summer. Incredible.
What we see for the first time is how the oceans and the land behave at the same time through time for 20 years. We've never had data like these before. Half of our photosynthesis occurs in the oceans and the other half on land. And having these data to show both at the same time, day after day, month after month, year after year for 20 years, is a great tool to study life on Earth. NASA has observed many aspects of the coupled land-ocean atmosphere system and how they interact. For example, we see that with warmer surface temperatures, the growing season is getting longer at higher northern latitudes, and spring is coming earlier. With satellite data, we're able to map this continuously across the Earth's surface and across the United States and across Alaska. Before that time, you had to rely where you had weather stations, and so you had points here, points there, but you never had continuous data like these. So using these data, we can look over very large areas and see regional effects, and sometimes these effects are positive in that nothing bad has happened. So it's only with these data we're able to do this over all these areas at the same time. And this is made possible by the use of Earth viewing satellites, which orbit the Earth day after day, month after month, year after year. And these data are the basis for saying these things about Earth with confidence because we measure them.
The view from space is opened our eyes to so many different things. You can see transitions from La Nina to El Nino, represented by huge blooms of life across the Pacific Ocean at the equator, bigger and wider than the United States. You can see greening of the Arctic, you can see earlier summers, later winters, and you can see the emergence of harmful nuisance algae.
Charting the carbon dioxide cycle through the atmosphere, land and ocean is essential to understanding the environmental changes that man is driving. Higher carbon dioxide, or CO2, in the Earth's atmosphere appears as red and yellow, while lower than average CO2 is shown as blue. The pulsing of the data is due to the day-night cycle of plant photosynthesis. As CO2 is lifted away from the surface, it is rapidly spread around the world by high-altitude winds. CO2 builds up in the northern hemisphere winter when plants are dormant. By summer, photosynthesis draws massive amounts of CO2 out of the atmosphere, resulting in lower CO2 throughout the northern hemisphere. The growth and decay of vegetation in the northern lands causes the seasonal change in atmospheric CO2. Long term, however, it is human activity that is increasing overall CO2 levels.
So 2017 was the second warmest year ever recorded and the warmest non-El Nino year. That makes 5 of the warmest years ever recorded just since 2010. And NASA scientists have taken weather station data from over 6,000 stations, and we've connected the dots to understand how our Earth is changing. In this animation, you can see those warmer temperatures growing as we look at how much the high latitudes in places like Alaska have warmed since 1950. So across the globe, we're seeing a consistent trend towards warming, but with twice as much warming across the high latitudes like Alaska.
This rapid increase in overall global temperatures is clearly defined when satellite data is added to the model.
The ability to expand your senses into space, compress time, watch visualizations like these, see how the ecosystems of land, ocean, atmosphere, ice all interact, and then be able to rewind it and watch it again and again. It's amazing.
Ask any astronaut. When they look down at Earth, they see a single environment. No borders, no claims, just a single planet which we all have to rely on. With this data, scientists can check up on the health of the planet. One primary concern is the ozone layer.
So we know the Montreal Protocol was a huge success. This was signed in the late 1980s when scientists and policymakers from around the world gathered together to try to save the ozone layer.
The chemicals they regulated persist in the atmosphere for many decades. They thin the ozone layer and they create a seasonal hole over Antarctica. They basically take away part of our planet's natural sunscreen, and that increases the risk of skin cancer and damage to plants.
Scientists have projected the ozone hole will disappear almost completely by 2075, but several factors could delay that outcome.
There are some industrial compounds that are not banned by the Montreal Protocol, but as they enter the atmosphere, they will also hurt the ozone layer.
But the unregulated compounds have a short lifespan in the atmosphere, unlike the chlorofluorocarbons that were originally regulated. So they have a short-lived impact on ozone, and we don't think they'll delay recovery by more than a few years.
We projected by 2050, more than half of the ozone-depleting compounds in the atmosphere will come from long-lived substances banned by the protocol.
Because these compounds stay in the air for such a long time compared to the unregulated short-lived compounds, they will have a disproportionate and lingering impact on ozone. Any non-compliance with protocol can have significant consequences.
And the really big uncertainty in ozone layer recovery is climate change. There are many naturally produced ozone-depleting substances that are emitted by the oceans. And as the oceans continue to warm due to climate change, those emissions will increase, and that will further delay ozone recovery.
Scientists want to understand better how climate change will affect ozone recovery.
This is a hard problem. As a scientific community, we need to work on this major issue. We now have a powerful new tool to simulate atmosphere and its interaction with land and ocean to study this issue. And that's what we're going to do.
At the top of the world, however, the Arctic ice continues to shrink.
Sea ice is the ice that grows and melts within the Arctic Ocean. It grows in the wintertime when it gets cold and melts through the summertime. And so it doesn't raise sea level, but it's very important for the global climate system because the ice is very bright and reflective, reflects a lot of the sun's energy that comes in during the summertime and helps keep the Arctic cooler. It's like a refrigerator for the global climate system by keeping the globe cooler than it normally would be without sea ice. And as we lose the ice, it's like we're opening the refrigerator door and not cooling things as efficiently as we used to.
Constant observation since the 70s lets us see a trend.
The Arctic sea ice has been changing quite rapidly. We've seen a decline over 35 plus years of a record. The last 15 years particularly, it's been accelerating. So really, it's become a matter of when, not if, we lose the Arctic sea ice, because we have a lot of warmth in the Arctic. It's going to continue to warm. We're going to continue to melt sea ice. There's uncertainty as to exactly when that will happen, but sometime in the not too distant future, faster than we used to think, the Arctic Ocean will be substantially ice-free by the end of summer. Arctic sea ice is not the only place we're seeing big changes. We're also seeing big changes in Greenland, which is the big mass of ice on top of the continent, and we're seeing more and more melt. We're seeing ice calving off as icebergs, so we're seeing big masses of ice loss over the last several years. That means that ice is going into the ocean, that's raising sea level, so that's going to have big impacts down the road as we continue to lose more and more ice from Greenland.
Ancient air bubbles trapped in ice enable us to step back in time and see what Earth's atmosphere and climate were like in the distant past. Today we stand on the threshold of a new geologic era which some term the Anthropocene, where the climate is very different to the one our ancestors knew.
We can see that a warmer world means that there's an impact for warming temperatures in the Arctic, melting sea ice. That sea ice leads to larger sea level rise. So NASA scientists are on the ground in airplanes and using our satellite data to understand how what starts in the Arctic doesn't actually stay in the Arctic.
The hope is that all this data collection will mean that real-world problems can be reassessed and new angles explored. A case in point, dolphin and whale stranding. Could this accumulated satellite data help address the problem? Cape Cod in the US state of Massachusetts is home to one of the most frequent marine mammal stranding sites in the world.
If we can get there quickly and provide supportive care, they have a much better prognosis in terms of survival.
Scientists know very little about why these mammals strand, and only a quick and efficient response in these events will save lives. Katie Moore works on the front line and has fine-tuned rescue efforts.
If we can develop an algorithm that pieces together the different variables that may be causing mass strandings or driving mass strandings, then we have the ability to then prevent them. We can have teams that are out on the shore looking for animals in those hot spots, knowing that all those variables have come together and this is the likely point in time where we're likely to see it. But we can also have teams ready to respond so that if they do strand, we're there that much faster and more animals will survive the event.
Marine biologists from the US Bureau of Ocean Energy Management were also looking at this problem.
For the large proportion of these strandings, the animals are across the ages, in pretty good health, and there's no really immediate evidence as to why they actually strand.
One possibility is geomagnetic perception, the ability to navigate using Earth's magnetic field, which is believed to be used by marine mammals. Could changes in the magnetic field confuse the animal? Geomagnetic pulses or storms can be caused by space weather.
Geomagnetic perception is one of the theories, and I thought, well, if a magnetometer can pick it up, maybe the animals actually can pick it up.
Dr. Reed consulted with NASA at the Goddard Space Flight Center.
The coolest thing was that we realized that nobody had really taken a cold, hard data science analysis look at the problems.
What we were trying to look at here was if there was a potential driver or relationship or correlation between the occurrence of mass strandings and any solar activity.
The data that we have correlated or analyzed so far is information about the local geomagnetic conditions. We have long data records from geophysical observatories of the local geomagnetic field variations and marine mammal stranding.
Their analysis was inconclusive. They needed more data from other environmental conditions.
Easy fix correlation between a geomagnetic pulse and a stranding doesn't seem to be very evident, but what it does show is that there are multiple variables involved in this equation, and that the geomagnetic storms could just be one very small part of it. Significant still, but it looks like there are multiple oceanographic and environmental elements.
With more data in hand, it was time to expand the team. They recruited statisticians and the expertise of NASA Earth Science data analyst and oceanographer Erdem Karakollu.
A data set, no matter its shape or content, always has a story to tell. Trying to figure out how different data are connected, I think, require a wide diversity of skills and background knowledge.
For example, I'll be explaining how a mass stranding occurs and how we respond to try and understand why I'm presenting the data in a certain way. And my colleagues from NASA will look at me and ask questions that I wouldn't think to ask because I take for granted my understanding, and they're coming at it from a totally new angle with no background.
These data sets may reveal a pattern, allowing scientists to predict the likelihood and location of mass stranding before it happens.
We've really just sort of slowly peeled the first layer of this onion back. And I think that there's so many more layers that still need to be addressed and looked at. And I hope that we can actually find additional collaborators, additional funding partners to really bring all the data that's really available to really give this the study and the scrutiny that it deserves.
And we are also going to make all these data sets available to the entire scientific community so that we can utilize the entire scientific community to take an attack and approach this problem.
I think that there will be other things to take and run with, get new ideas, maybe add more data. And I'm hoping also that it will be a model for how projects can then be open to the wider public.
The ability to release animals after they've stranded is tremendous. When we do that, I mean, that's the best feeling in the world after all of that hard work.
Those questions that seem unanswerable, if you give them time and support and effort and put people on them, we can do amazing things.
Data from satellites reveals the interconnection between air, sea, and land. This is a visualization of three aerosols: dust, smoke, and sea salt. The Calypso satellite data reveals in 3D how dust from the arid Sahara Desert is lifted by the winds each year and transported nearly 5,000 kilometers across the Atlantic Ocean. Some of it settles in the Amazon basin, the largest rainforest on the planet. Sahara dust contains phosphorus, an important nutrient for plants. Calypso shows that on average, 182 million tons of dust leaves Africa each year. When the Sahel was dry, the dust transport to the Amazon in the next year would increase. When it was wet, dust transport would decrease. We can now track global precipitation, wind currents, cloud cover, and ocean temperature. Satellites have detected a shift in phytoplankton populations across the planet's 5 great ocean basins, showing the expansion of biological deserts where little life thrives. Diatoms are one of the most abundant types of marine phytoplankton, but a new 15-year-long NASA study reveals global populations have declined. Diatoms, like all phytoplankton, have chlorophyll, the same photosynthesizing pigment as plants. They occupy the surface of the ocean, where they harvest light from the sun. In large numbers, Diatoms form colorful swirling blooms that can be seen from space. According to the study, significant decreases in populations, shown here in red, are mainly in the northern hemisphere.
Diatoms rely on nutrients such as nitrate, silicate, and iron to reach the surface layer where they live. What the study shows is that the availability of these nutrients has changed due to the way they cycle within the water column.
Diatoms occupy the surface area of the ocean called the mixed layer. Nutrients collect on the ocean floor and are cycled up to this layer. Various physical forces can cause the depth of the mixed layer to become shallower, so that fewer nutrients reach the diatoms. Without these, their populations decline. This map shows areas on the globe where the depth of the mixed layer shallowed.
It's hard to pinpoint exactly why this change have happened. Things like wind, circulation, and temperature can affect the way these nutrients are brought to the surface layer. We hope a longer study can yield more information on whether these changes are in fact a trend or variability.
Next-generation satellites are reaching orbit now to continue this important work. They will collect data, maintain observation continuity, and allow scientists to track the changes in our environment. They can then model dynamic simulations to better understand this unique planet and the myriad of life forms that rely on it.